Okay, here's the second video in our programmer project. We're going to look at the C code here. I had a heck of a time doing this. I thought it was going to be at most a 3-day little project, easy to do. Convert my already working assembly language code into C, no problem. I had problem after problem and issue after issue. So this is a lot later than I wanted it to be. Had problems with the programmer, I had problems with the microchip IDE, I had problems with C. It was just a nightmare, and I let it get to me and I let it slow me down. But anyway, I finally got to a basic usable state where it does program apart, and so we'll take a look at where we're at. Okay, basically I just try to go over the things that have changed, and which isn't a heck of a lot, or maybe a heck of a lot, I guess. I defined a bit here for the data direction register for the data pin to the target, so we can write and read from the target. So this controls the tri-state control line. Added some more functionality. And here's the prototypes. Our main hasn't changed at all. It's still real short and sweet. The initialization, I don't believe has any changes at all. We may have moved port B. I can't remember if that was on the previous video or not. We may have moved. The control lines were all on port A, and I have moved them to port B, so that may be a significant change. Interrupts, real simple, does the same thing. I still have not checked if it's saving the registers I want to have saved. I guess I'll find out one day. Here's some documentation that's moved around. Some of the documentation is moved for compilation reasons. Decode command. All the commands now have a actual function to do, instead of just some of them just went to break before. Here in the address initialization, this is for blocks that are of program that are separated by unprogrammed space. The program I'm testing is all one block that starts at 0. So this is really untested right now, but it's in here ready to go. Here we have our receive 2 bytes of the configuration word and program the configuration word. This part just receives the 2 bytes, and we call load configuration. We'll get to that in a second. Here's program target. This actually drives the data into the target chip that we're programming. This is all new. Basically, we check if we're in high voltage programming mode or not. If we're not, we enter it and erase the chip and set the high voltage programming status bit, so that we don't only do this once per call. This block, remember, gets called for every 240 blocks of data. I know you got a couple of nested while loops here, and basically it just sends a set of 8 program words to the target, and then sends the commands to program it. Now you'll notice they're both while one loops, and that's because the increment address command needs to be short-circuited. So here we test the counter and break out, short-circuiting the increment address. We can't always increment the address. That's important for the state machine and the target. And it was just the easiest thing to do to test the counter here and break out, so that we skip this increment address. And the same thing is true here. We break out here in order to skip the increment address. It wants the address to be left within the block that it's programming. So in other words, the bottom 3 bits of the program counter aren't even considered, and the remaining upper bits are, and that's how it tells what block to burn. So you have to have your address remain within the unprogrammed block that you're about ready to program. So I found out this is the easiest way to do it, the cleanest way to do it. Just have the while one and short circuit them with these breaks. And all we do here is prepare the data bytes to fit into the 16-bit format. That's with the start and end bit, and the 14 bits are centered within the 16 bits that we transmit. And so we set that up, transmit the 2 bytes, and when we've done that 8 times, we go ahead and send the begin program, the mandatory delay, the end program command, and we see if we're done yet. Here's where we do the load configuration for the, this is the configuration word of the fuse bits. Basically it's real straightforward. You do the load configuration command. This actually puts the address at hex 2000. Now you can't increment the address whatever you are and get to hex 2000. It'll always roll over at 1FFF and it'll roll over to 0. So this command is the only way to get into this configuration area. Now the actual configuration word is at 2007 hex. So when you execute this command, you're put at 2000 hex. Now you have to write the first ID location, which is at 2000. You have to write something to it. It really doesn't matter what, but if you don't, even if you don't want to program it, you still have to do these two writes, or the state machine gets confused and you can't program the configuration word. So then after you've done that, then you can increment the address just 7 times to go from 2000 hex to 2007 hex. Issue the load program command, send your data, issue the begin erase programming cycle, and that's got a mandatory delay of 10 milliseconds. Now we want to read it back, so we call word read. We'll get to that in a second, and we send that back. Instead of an ACK, we send back the 2 configuration word values for verification at the host. Okay, here's word read, and this is where we read from the target, and this is also going to be used, we're using it for read the configuration word. It's also going to be used for reading the program back for verification, which we don't do yet. And it's pretty straightforward. You issue read program command. I got a assembly no op in here to stretch the clock a little bit. I turn the bus around so that the target's not going to drive the data bus when I clock it. And then we count 16 bits, get our 16 bits out, accumulate those, and when we're done we set the data direction back to an output on our programmer. And that's all there is to reading the word. Okay, here I've added for each of our erase functions, chip erase, program erase, and the data area erase. I've created a external, that's what the X is for, an external command from the burner. Now, so you can do separate erases on command, and otherwise it just uses the erase internally. And the main difference is it returns an ACK if you get an external erase command, and no ACK if the program's just doing it itself. So we also enter programming mode do the erase and exit programming mode. And it's basically the same there's one for program erase and one for the data or double EEPROM erase. They work about the same way. And lastly, I've straightened out enter and exit programming mode a little bit. Keep track of status, control all the signals, and set up the program counter for where we think the target address is at. And that's about all the changes for the C code. Okay, about the only thing that's changed in our Python host code is handling the configuration word, programming the fuse bits. Now it's a special case, and in this file, the hex file that I'm sending, it's on the next to last line. It's got an address of 2007 hex. Actually, it's twice that. It's divided by 2. Remember, the Intel hex file counts bytes, and we want to count words. So we check for each line for a line address of 2007. If it is, we just go ahead and send anything that may be in the instruction bucket, and no guarantee we've programmed all the code yet, so we go ahead and do that first. And now we assume that this is the only data on the line, and for this file it is. And for this file it's going to be at index locations 9, 10, 11, and 12. Where do I look at 9 and 10? Oh, here. So here I make the two words to send over to the programmer. And after we do that, I just wait for the 2 bytes to come back. Remember, so there's 2 UART reads to read the high byte of the configuration word and the low byte of the configuration word. And that's really the basic change here in the Python code. There are some places where things a little bit has changed, nothing significant. Mostly it's debug printouts that have changed. And so if you're interested in that, you can just look for it yourself. But hopefully this, I'm wondering what will happen here when, like if I wanted to specify ID locations, which there's 4 ID locations that actually hold a nibble each. And so if I specify, I don't know how to do that yet in C, but that needs to be tested, because it might put them on this line with 2000 line, and this might have to change if there's any more than data on here than just the configuration word. So I don't know, I just have to see. But anyway, this is usable now. It does the bare minimum. If you want to play with it at all, here it is to play with. Or you're interested in how programming works. This is it. All the code is in the second page of the relevant web page output, the programming pages. And so the code, you can download the code, both the C and Python host code, also the hex and ASM for the file that we're downloading to the 877A, and the schematic will also be on the website. All that'll be in the one download, so you can get that if you're interested. Alright, so last time I don't think I showed the breadboard at all, but here's the mess I'm working with. We've got the Max 232 here to connect to the PC, RS-232. Here's the PIC. It's the 2550. It's got USB support, it's the main thing, and a lot of memory that we'll be using in the future. Not making any use of that right now. I had to add a regulator up here, just a little 7805. Got 13 volts coming in, going over to programming, to M-Clear on the target processor here, the 16F877A, and I was taking the high voltage off of pin 2 of the Max 232 here, and that put out about 8.9 volts. And even though it was under spec when I was doing this in the with the machine code, it worked fine the whole time. When I went over to C here, I don't see how it made any difference, but I had to go to 13 volt input. And I think, well, one thing I did, I blew this transistor fooling around with the board, and he switches the high voltage on and off. And so he's probably got less gain than the other transistor I had, and I haven't even looked at what he's putting out, but he's putting out enough to program the chip. What we're going to do here is power this guy up. Oh, and the 877A here is connected to this DL1414 display. This is the only indication that this guy's running at all, and that's all he does is write 877A to the display. So right now we'll power this baby up, and you won't see anything. Oh, well, he's running. Okay, he is programmed. So there he puts out his. Cut the light off. You can see he's that'll come into focus. Come on, little guy, you ain't gonna do it. There it is. You can barely see 877A on there. Get our light back. Okay, and of course we don't have all the switching and cool thing. The way we install the programmer here is to plug in this wire. And we'll turn her on. That's holding them in reset. We'll go over to the PC and erase the part. Okay, I'm going to have to shoot this off the screen again. I hate to do it, but this is my development machine, and it's got the serial port to the breadboard, so I'm going to have to shoot it off the screen here. We're going to start our Python program, download.py, drag it back up here, and we just need to well, let's go ahead and request status. Whoop, let's select the hex file. Always forget to do that. That's our annoying GUI behavior. So this is the burner test program we're going to put in. This is the one that just displays the 877A on the little 4-character display. Now we can request status. And we got an up 1 and everybody else is 0. So that's working good. So let's do a chip erase. And we get chip erase was acknowledged. And let's go over and look at it and see that its program's gone. Power down. Take a programming wire off of pin 1. Power him back up, and nothing. So power him back down. Plug our high voltage programming wire in, and we'll send him the programming command. Okay, now we verified our program is not in there, and so let's go ahead and let's request status, make sure we're talking. That's good. Let's go ahead and burn that file. And there's our code we sent out. Still have a lot of debug messages in here. Our CRC matched. We wrote the configuration word 3F3A, and we got it back. That's 3F and 3A, but I failed to put it in hexadecimal. But you can look that up. That's 3F and that's 3A. And good status and finish. So let's go see if that worked. Take our that's also reset, so take out our control wire and turn them on, and we should have and there's our code running again. And there's our 877A. Well, here's the scope trace of our data going out to the target 877A. Basically got a capture on 10 milliseconds per division here. The first thing that happens is we go into programming mode, which is PGD, PGC going low, and then the programming voltage coming high. This is on 10 volts per division. Looks like we're right at 10 volts. So my little transistor's eating up 3 volts. The timing is supposed to be 100 nanoseconds, so we're 2 microseconds per box. At 500 nanoseconds box, so we can see we're about a microsecond, well, a little under a microsecond, about 750 nanoseconds. So that's a lot longer than 100 nanoseconds. So no trouble going into program mode there. That's just executing 3 instructions in a row. Let me see, the first thing we do is issue an erase, chip erase, which is a 1F. And the trouble with with this, the format is least significant bit first, so you have to kind of read them backwards. There's an unused bit at the end. Otherwise, they're 5-bit commands. So that's 1. We can see we have the unused bit is 0. We have 1 for the 1, and 1, 2, 3, 4 ones for the F. The date is latched on the falling edge of the clock. So there's our 1F, and there's the chip erase. And the chip erase requires a delay of 10 milliseconds. Right now we're on 2 milliseconds per division. There's when our command goes out. We wait 2, 4, 6, 8, 10, 11, probably 11 and a half milliseconds. So we got plenty of margin on that. Then we start sending our data, and I'm not going to look at every bit, but there's our data going out. We program 8 bytes at a time, or 8 words at a time. So we can see we have, if you can see the little gaps, we have 1, 2, 3, 4, 5, 6, 7, and 8 words going out. When at the appropriate amount of time, which I think is a millisecond, and This is waiting a little over 2 milliseconds, so we have margin there. So we can improve our timing. We're not sending a whole lot of code. Just that many groups right there. That's all our data going out. And then we have this little guy. Whoops, what'd you do? This command here, which is should be begin programming, and that should be, I believe, 18. No, 1. What is that? That's 1. It's a blank 1. 1, 2, 3, 1, 7. What is 1, 7? Let me check on that. Okay, 1, 7 is the end programming command. We went a time period there. Then our next command is all 0. That's easy to decode. All zeros is load the configuration word. And we first have to, that requires two 16-bit words, and these are required probably for the state machine in the part. You have to issue the load programming, and even if you don't want it, this is an ID location. It sets the address to 2000 hex in this part, which is the first ID location. There's 4 ID locations, and even if you don't want to program it, you're going to have to send it some data, because that's what the state machine wants. That's implied in the documentation, but it's not really stated that. And if you look at the timing diagrams, it really doesn't indicate that you have to do that, but you do. So after that, after those 2 bytes, we then want to move the address to where the configuration word is, which is 2007. So we have to have 7 of these little guys, which are increment addresses. We have 1, 2, 3, 4, 5, 6, 7, and that should be the last one there. So here we have the load program command, which says we're going to write a 14 bits to the configuration word. Here's our configuration word. That turns out to be there's a start bit and a stop bit at the end. So first bit actually starts here at the second falling edge. Of course, we've got to read this way because it's least significant bit first. So it's 3F, and it's a 3A, and just take my word for it. We don't have to look too close. And then after we do that, then we send it a 8, which is begin erase programming cycle. And this erases the location if it's not erased, and programs the word in. And after that, we have a long delay, appropriate delay. And the last thing we're going to do is read that configuration word back. Blank, nothing, 8, 4, okay, 4. A read program, and we're going to read that data back. And you can see we turned the bus around, and actually this is the target now driving the bus, and I'm sending out clocks manually here. You see the difference in the way the clocks are structured. And we read back our 3F3A. So that's it for transmitting the data. Okay, well, thanks for watching. I don't know when I'll get back to this project. It'll probably be a little while. Next thing I want to do, besides just fixes and stuff that should be done, is to do a atmel, probably a 328p. So, well, thanks for watching, and we'll see you next time.